I recently made a project to turn a BBC microbit into a very simple CPU. This behaves a little bit like some of the early microprocessor development boards like the Kim1 or the Science of Cambridge MK14. And although it could only add two numbers together, it did behave quite a lot like one of those early computers. So instead of being programmed in a high-level language like MakeCode, Scratch, Python or BASIC, we program it using binary codes, and each binary code represents an instruction with a piece of data attached or just a piece of data. And when the programs run, the CPU function in the program fetches each instruction in turn from memory, it decodes the instruction, it decides what it means, and then it executes it, it carries it out. It keeps track of where it is in the program using the program counter, which is displayed on a binary display on the top row. The contents of each location are displayed in binary in the middle row, and it carries on fetching, decoding and executing instructions until it reaches a halt instruction, and it can output contents of its register, its accumulator, basically the results of its calculation in binary on the bottom row of the microbit display. You step through the program using button B, so you press through and it executes one instruction at a time. There's no clock in our CPU, our microbit CPU. You do it manually, and because the programs are very short, that's fine, and it's nice to see the program executing and the lights changing on the display. If you just step through normally, pressing button B, it just shows you the contents of the memory. It doesn't execute the instructions unless you put it into program run mode. So you press button A, this light here lights up, and that means that now your instructions will actually be executed and they will be carried out. Well, that's all well and good, but we could only really add two numbers together, and the reason for that was I'd limited myself very much by having the operation code, the opcode, and the operand, the data, in one 5-bit word. So I've created a new version of this project where I've kind of split things out a little bit more than that. And the reason is I want to be able to multiply two numbers, and I tried to think of what the simplest possible algorithm for multiplying is if you haven't already got a multiplication function. Now we know we can do multiplication by repeated addition. And here's a MakeCode program that does that. It puts two variables. I'm going to multiply 6 by 7. It puts it in two variables, x and y, and then it uses a loop here. And as long as y isn't equal to 0, it keeps doing this. It keeps changing a, my accumulator, by x, so it keeps adding 6 to the accumulator. And then it takes 1 away from y, and when y gets to 0, it means it's added up 7 lots of 6. Y0, this loop stops running and it shows the answer on the display, and that will work. That will multiply 6 by 7 and show 42 on the display. Now if I want to implement that on my microbit CPU, I'm going to need to do something a bit new here. There's a few things I need to do. I need to be able to decrease a variable or a register or a memory location by 1. That's called decrementing. It's kind of the opposite of increment. So if you increment something, it goes up by 1. If you decrement it, it goes down by 1. But much more importantly than that, I need the ability to loop over sets of instructions. Now, I can't do that with my previous microbit CPU. And the other really important thing is it needs to be able to break out of the loop when something happens. So basically, this is an if statement in another form, really. If something is true, if y is equal to 0, this loop actually stops. So I need the ability to make a decision. Now, that's really important. The idea that you can make a decision based on the state of something, in this case when something reaches 0, is fundamentally what makes a computer rather than just a calculator. It's, for example, what separates Charles Babbage's analytical engine, his theoretical machine he never built, from the simpler difference engine, which was basically just a glorified adding machine. So it's that ability to make these decisions takes you from a calculator, from an adding machine, to something a bit more like a general purpose computer. Now, I'll have a quick look at the MakeCode project now for the improved CPU. It's getting quite complicated now. I've got a lot of new functions, but the really important ones that I've added are this one here, jump if not 0. So I've got the ability now that if a calculation results in the answer 0, we set a 0 flag. The program will know if something's reached 0, and it can make jumps, it can do a loop. So with that instruction 0 1 0 0 0, it will keep jumping back and repeating the same bits of code until something reaches 0. Let's have a look at our new program. So we've got a slightly new program now, if I can find it. So my program sits in memory. It's written in binary, and the program lives in an array. So I've got my program written as it's written as text, really, in a binary form. In an array, and here's how my program works. So my first instruction is to add the contents of memory location 8 to A. So that's down here, so it's adding 5 to A, my accumulator, and this number here is the address. It's telling the instruction where to go and fetch the number from. So it's not going to add that number, it's going to add the contents of the memory location that represents. So it's going to go down to memory location A, find the number 5, and add that to my accumulator. It then decrements the number I'm multiplying it by. Here I'm multiplying 5 by 6. So it's going to reduce 1 from this number here, which is 6, held in memory location 9. And then, if my 0 flag hasn't been set, it's going to go back to instruction 0. So it's going to keep doing this all the time until basically this gets to 0. Then it's going to stop, or before it stops rather, it's going to output the answer on the display, and then it's going to stop. Right, let's try this out now. I'm just going to reset the microbit CPU just to make sure everything's set back to 0. I'm going to put it into program run mode. It makes a little beep to say that I've started. And now, as I'm stepping through, this is like my clock cycles stepping through the program. So you'll see the program counter at the top scooting back over the same memory locations over and over again. And it should do this, if it's multiplying 5 by 6, it should do this 6 times before it halts. There we go. It's halted. It's got to the end of the program. My program run flag has gone off, and it's displaying the answer 11110. Right, let's call up my calculator. Let's get my programmer's calculator up. I'm going to put in 11110, and it's 30. It's decimal 30, so it's actually worked. It has multiplied 5 by 6, and it's come up with the answer 30. So that works. Now, there's lots of things, more instructions I need to add to this, and to develop it to do more things. I can't subtract at the moment. There are many other operations that I might want to do, but it's a fun way of extending that project, and I've actually can do something useful now. I can actually multiply 2 numbers together, and I'll be developing this in the coming weeks. And if you've got any ideas for instructions I should add, or programs you think I might be able to run using my microbit CPU, I'd love to hear from you.